All right, hello, welcome to video 28. This is going to be on water resources, kind of a little introduction on how we can degrade the water cycle and reduce our available fresh water. So we're going to start off just with the water molecule itself. This is a covalent bond between hydrogen and oxygen. And so what covalent means is they're sharing electrons. One of the unique properties of water is that it's polar, meaning that they do not share equally. The oxygen is more electronegative, and so it'll pull the hydrogen's electrons closer to it, and it creates this slightly negative side, while hydrogen ends up slightly positive, having that one proton without any real electrons nearby. This is a very unique property that is beneficial to life here on Earth, and so when it freezes, this would be frozen water, also known as ice, you get that positive and that negative side lining up from all the water molecules, which creates a space, a little gap in there that can be filled by air. This is good because that means ice will float. And so we're looking at a pond. The top layer of the pond will freeze first, and it'll kind of create this insulating layer for the liquid water below. That liquid water below is, of course, where the fish and the plants and stuff can live and survive through the winter. If we did not get these air pockets, as it froze, that ice would sink down to the bottom and kind of freeze from the bottom up, creating a pond that was completely solid, and you would have no survival of those fish species. So it's good that this happens. One thing that we're going to talk about throughout this, especially as we're testing water quality, is this unit PPT, also ppm, and ppb. ppT is parts per thousand. And so if we're talking about seawater, if we were to go scoop up a liter of seawater, that liter of seawater would contain 35 grams of salt. And we could boil out all the water and we'd be left with 35 grams of salt behind. That means the remaining 965 is all water molecules. And so when we say 35 parts per thousand, it means if we take 1,000 parts of water, 35 of them will be seawater. ppm stands for parts per million. ppb stands for parts per billion. So these would be used for lesser concentrations because you're talking about a bigger amount of water compared to the part we're interested in. And so we might measure oxygen and dissolved oxygen in ppm, parts per million. Our water in general, as we know, is mostly ocean water, seawater, unpotable to us and most animals. And so we're looking more about the fresh water for this. What do we get our water from? Of the 2.5% roughly that's fresh water, a lot of that's locked up in ice caps and glaciers. More of it's locked up underground or is polluted beyond what we can use. And so it leaves a very small percentage of the pie for us to use as water. It's not necessarily a bad thing because this does come out to a couple million liters of water per person on Earth. The big issue with fresh water is the distribution and kind of the degradation of the cycle of water. And so this is what this video is going to get into today. A couple terms to know. I mentioned a few of these already, but make sure you go through and look at them and know what they mean in case I just kind of say one later. I'm kind of expecting you to know these terms. This is our watershed, and so kind of how it should naturally run. We're going to get water entering the watershed via precipitation, and there's several trillion liters of water every day that are rained on just the United States alone. And so the water that's landing has a couple different options. Some of it will run off right off the bat. This is especially true with heavy rains that is falling faster than the ground can absorb it. And so that water will enter streams and go down to lakes and oceans. And we don't really get a chance to use that water. The plants certainly don't get a chance to use it. And we don't get a chance to use it as people. The rest of the water is going to recharge the aquifers, meaning it's going to hit the ground, be absorbed in the ground. This water would be available for use of plant roots as it's moving through the soils, but some of that's going to make it down into the aquifer. And there's two types of aquifers. There is a confining layer here, which is rocks that water cannot pass through. That confining layer creates a confined aquifer below where water cannot move back up. And it kind of is locked there for a really long period of time. This will really clean and filter the water as it moves down through the soil, and so it's really high quality fresh water. Now, we can drill wells down to extract it. This here is an artesian well, which means we need to look at the altitudes of where the water enters, which is up here in the hills, and where we're drawing it out, which is down here in the valley. And so there's water pressure pushing down just due to gravity trying to pull that water in. What that means is as soon as you create this artesian well, water is going to flow out of it naturally without needing any kind of mechanical pumps because gravity is drawing it up and out, just like how we siphon the fish tank in the classroom. The other type of well is one that's accessing this unconfined layer, and so the altitudes of these waters and the well are different, meaning we need some kind of mechanical force to drag the water up, and so that would be our pumps. And this unconfined layer here, we're going to get some horizontal movement to and from this lake, and so it's going to be easily accessible to us and plants and stuff because it's able to move around through the soil. What do we use water for? So the bulk of our water is used for agriculture, mainly irrigating, keeping crops alive, especially in arid regions where there's not enough water to support plant life. The rest of it, the bulk of the rest of it is used for industry, things like creating wood products, power generation, metal production, that kind of stuff. And then the remaining part is domestic and municipal use, things like brushing your teeth, flushing the toilet, taking a shower. That would fall under municipal use. What happens to water? So if we're talking about a natural kind of climax ecosystem here, a lot of that water is going to be evaporated back up. That would be our surface waters, our lakes and rivers. Also, the water that's in this top layer of soil that these plant roots have access to, that will be pulled up through the plants and then enter the atmosphere through transpiration. As the plants use that water for photosynthesis, it'll be released through their stomata and back into the atmosphere. The bulk of it, though, does enter the groundwater, and so it's going to recharge the aquifers and kind of be staved and stored there for later use. When we build on land, typically we're laying in a layer of concrete down. That layer of concrete does not allow water to pass through it, and so what happens is over urban industrialized areas, the bulk of the water is just running off the surface through this surface runoff. This can be through storm drains, it can be off roads and buildings, and it's kind of lost to us and lost to the environment. It's not used to growing plants. Typically, it's going to be pushed into the rivers and right back into the ocean as quick as possible. Because if we have houses built, we don't really want them filling up with water, or we don't want our yard to be mucky and wet. So we're going to run that water off as surface water. The problem with that is we get very little, by comparison, entering the groundwater, and so you can create a slower recharge rate to the groundwater in areas where you have probably a very high usage rate. Also, a lot of that water is going to kind of sit on the surface and be evaporated. However, the transpiration is not really happening because there's not a lot of plants growing in the concrete. Floodplains and levees, so this areas around rivers, like the Mississippi River, for example, is very fertile land because you have this long history of having running water there. So there's a lot of plants, a lot of organic material to decompose. You get very rich soils. Also, periodically, that land would flood as the snow melts in the headwaters, or as you get seasonal rains that cause flooding. That flood is going to kind of turn over the soil. It'll kill some smaller plants and kind of keep the forest clear, just like a brush fire would do. It'll also distribute the nutrients and the sediments a little differently and expose some new habitats. Generally a very good thing. When people come around, we don't want that river to flood because we want to take advantage of the land around it. That fertile soil looks great for farming, plus it's very easy to draw irrigation water straight out of that stream. And so we build these levees in the floodplain to control the river and prevent it from flooding so we can live happily nearby. The problem with our levee building strategy is that it creates these very deep channelized rivers that move very, very quickly. And the speed of this is a bad thing because it's going to increase the erosion around it. It's going to carry a lot of sediments downstream. It also doesn't give any water to that surrounding area, and we're not getting a refresh of the nutrients and sediments around the stream. So it's just kind of flowing and flowing and flowing. What we can do is that we build smaller levees but spread them out wider, kind of creating this artificial floodplain in between. That water, by taking this non-straight path, is going to move much slower. It's going to be much shallower, and it's going to be much healthier. You're not going to get the erosion that you will up here. It also will be able to periodically flood and kind of expose new fish breeding grounds and things like that. They also cost less to build because you don't have to move as much soil to build a smaller levee, and you get that kind of natural ecosystem in the middle there, and you still have access to a good bit of that prime farmlands nearby. One big problem that we had with our levees was in 1993, where we had extensive rains and snowmelt that flooded the Mississippi River basin. And so it caused a lot of problems. The real big environmental issues here was that the farmlands that flooded, we lost a lot of those pesticides and agricultural chemicals, fertilizers and whatnot, all the way down to the Gulf of Mexico. And it also allowed this invasive species, the zebra mussels, to kind of migrate themselves up further in this ecosystem and kind of spread out throughout the watershed. The main reason why this happened is, one of them, we drained a lot of wetlands to build farmland. The wetlands in times of flood kind of act like a natural sponge. There's a lot of plants there and a lot of kind of soft, porous soil. And so as that flood comes, it hits that large area of wetland and it really slows the speed of it down. It soaks up a lot of the water and prevents it from really becoming a problem. Now, if you're replacing that with farmland, it allows that flood to keep building and growing. We also built on the floodplains, so if you're building your house in an area that historically has flooded seasonally, you might have an issue with floods down the line, especially if you're building levees. That creation of levees, like we talked about here, if the levee breaks and that fast-moving deep water is able to escape, it can be catastrophic to the people that live nearby. One of our biggest problems comes from overdrawing surface water. So in Jacksonville, we don't really rely on surface water that much for our municipal fresh water, but there are areas of the country that rely heavily on rivers and lakes for their water sources. And so this can be a problem if we're taking out more water than we're putting in. Just like a bank account, if you're overdrawing consistently without letting it recharge, you're going to end up depleting that resource. And so we can dry up our wetlands, which is kind of our flood prevention or protection. We can also mess up the estuaries. If the estuaries, the freshwater flow down the estuary decreases, then that ocean is going to push saltwater deeper into it, and so that can kill a lot of those plants, which can lead to the slowing down of that estuary. Subsidence is an important thing to talk about. This happens when you deplete an aquifer. So if we picture this land, this would be our aquifer down here, and above it we would have rocks or bedrock. And what happens is, as the rock pushes down on the aquifer is going to push back up. And so this hydrostatic pressure keeps things pretty equal. The real problem comes if we build a lot of wells and we start extensively drawing water out of that aquifer. As the water leaves the aquifer, the aquifer's pressure, the hydrostatic pressure, is going to decrease because now you've got rocks with open pores, just air pockets in them. And so that downward force is going to lower the surface of the land. And that's what happened in the San Joaquin Valley. So this guy is standing here, and that's the height of the water the height of the land in 1977 when this picture was taken. You can see just how much higher up he would have been standing in these previous dates. And so that land is dropping lower and lower and lower as the aquifer is being depleted. And it comes from using up the water in the aquifer faster than it gets replenished. Another big problem with aquifer depletion is sinkholes. And so very similarly, this happens a lot in Florida, especially because we've got limestone bedrock. That limestone bedrock is very susceptible to acid. And so as the rain falls, it dissolves CO2 in the atmosphere naturally and is slightly acidic. And as it moves down through the soil, it carries that CO2 with it. And when it hits the limestone, it can actually dissolve these big caves of limestone. And if you lose too much of the stone below, or the water is not filling all the little pores in that very porous limestone, that hydrostatic pressure is going to decrease. And if it decreases too much, you get this sinkhole where the ground above collapses in because there's nothing pushing it and holding it back up. And so that's kind of how sinkholes are formed. They can also form from industry. So this sinkhole is formed by oil drilling. You can see the tiny little person down here on the screen, just how large this is. Again, we're not getting the pressure up on the land above, and so it just kind of collapses and sinks in. Saltwater intrusion is very important too, especially in coastal regions like Jacksonville. And the problem here is if we build a well in a coastal region, at some point that unconfined aquifer, remember that aquifer that's above the confining layer, is salty, right? That ocean water is able to move left and this water is able to move to the right. And so they kind of form this zone of brackish water somewhere in between saltwater and freshwater. If we overdraw the aquifer, the freshwater aquifer, it's slowly going to lift up that saltwater and change the interface and move it closer and closer to the mouth of the well. If we continue this up and we really significantly deplete our fresh water, that salt water is going to start entering the well. And at that point, you've kind of run the course and created a major problem here, because that well is no longer producing fresh water when you might have relied on it to do so. This is actually where we're going to end for this video, so thank you for watching. I'm going to leave this slide up on salinization of irrigated soils. We've talked about this, but make sure you're very familiar with this. It's also a big water issue, not just a food and soil issue. But thank you for watching. Please make sure you have notes and be prepared to discuss for class tomorrow. Thank you.